Welcome everyone. In this video I'm going to talk about the most recent updates of this coil winder project. So I did a lot of changes and I want to make a follow-up video to share these changes and hopefully give you some useful ideas to build your own coil winder or just copy this one. So either way, I hope that this video will help you in your project. So there are two parts which I want to talk about, or I want to divide this video, is the mechanical part. So that is basically the motor, the mechanism, and all these parts which make the coil. And then we have the electronics part, which is the motor drivers, the microcontroller, and the software. So I will talk about these in this kind of order. So first of all, I want to talk about the mechanisms. And I think the most important change in this, or one of the most important changes, is the feeder, which is here, or you can see it on a photo where it is more easier to see the different parts. So this feeder is a 3D printed part. So this is a very good opportunity to introduce you to today's video's sponsor, PCBWay. So PCBWay is known for their printed circuit board manufacturing and assembly services, but luckily they have other services as well. And here I would like to show you the 3D printing service from them, because you can use their service to reproduce my parts if you don't have a 3D printer. So this is their main page of the website, and you can go to the CNC-3D printing part and select 3D printing. So if you click on the 3D printing, you can see a few options here. And first and foremost, you have to select your CAD file, which has to be in STEP, STP, or STL format. And then once the file is uploaded and processed, you will be able to check it in a 3D format. So you will be able to see it in a 3D viewer. So just simply click on View 3D and a new window will open. And then we will see the model which we are going to print. So this is the feeder model that I'm using. And then you have to select some parameters like the quantity and the design units. So it is in millimeters, and the quantity depends on you, how many coil winder you want to build. And then you can select your favorite material. If you want a more sturdy material, then maybe nylon or ABS will be better. It depends on you. But furthermore, you can just use the same material as I used, which is the PLA. And then you can change the color of it if you want some other fancy colors. You can select different surface finish options like spray painting or electroplating and so on and so on. And finally, if you have some technical drawing, you want inserts or something else, then you can add those to your order. And with this, if you are a new user, you can also receive a $5 coupon, so it can make your first build a bit more cheaper. So I hope that you will find their services useful, either for this project or for your other projects. So coming back to the feeder part, I actually have another piece here. So what you see there is sitting like this. So this, let's say, bottom part of it, which is connected to the block on this ball screw, and then this other back plate is this here, which holds 4 different things. So you can see these 2 white felt discs. These are basically just these regular felt discs which you can buy for furnitures, for example for the legs of the chairs or tables. And I put it here to introduce some kind of friction. So what we have is that in the entrance hole, let's call it like that, the wire comes in, so that is here in the back, and then it goes somewhere in the middle of this part between my 2 fingers, so it crosses there, and then here there is a bearing with a wheel and a groove in that wheel. So actually this acts as a guide. So that is here. And then the wire turns back here where there is an identical wheel like this metal one, and let's say folds or turns back the wire, so it will exit on this part. So then the wire continues its way and it will meet another disc here to introduce another, let's say, fraction of friction, and then it will exit here. And in this block we have 2 holes. One is the main exit hole, and on the top we have another hole which I planned to use for a bolt or screw. So that will be sort of a fixing or stopping screw, because here you can either put in a nozzle for 3D printers, like this guy here, like I did here, or you can put some kind of tube there, which can be used as a guide for the wire, which will meet the bobbin here. So that's the, let's say, route for this wire. And for these discs, I made another 2 centimeter diameter. This is 2 centimeter, so 2 centimeter diameter discs. So that is put on top of this, and then I use the spring and then a nut to fix everything together. So if I tighten these nuts, they are similar than these, so they have these wings. Tighten them more, then I introduce a bit more pressure, therefore more friction on the wire. So this part is a bit experimental in a way that you have to get a feeling of the friction for different wire diameters and speeds and so on. But this is one of the main updates what we have here. And then of course I have another set of 3D printed parts. But before that, let's talk about this new guide. This was actually recommended by one of my viewers. So if you are watching this video, thank you. This was a good, yeah, let's call it investment. So this is a NEMA 23 stepper motor, and this is a SFU 1605 ball screw. And everything is integrated into one system. So this is basically one piece of linear actuator. And this moves the feeder back and forth based on the width of the bobbin. So if you have this kind of bobbin, it will move a little bit. But if you have a bit wider one like this, then you can see that it can move like 5-6 centimeters. So this is another new thing. And then this guide is also used as a support structure for the rest of the structure here. So we have some 3D printed parts here and here at the corners. So those corner pieces hold together the wall frame. So this C-shaped or U-shaped, now from that perspective, U-shaped frame and this linear actuator. And then I have a few 3D printed parts which hold together the things. I will try to show you here, and then I cannot really show without destroying everything, but there is a similar plate on the other end, so here, because as you can see, there is an additional 2 by 2 centimeter profile here, and then the motor is attached to that, and the similar happens here. So this bearing housing is sitting on top of a 2 by 2 centimeter profile plus a few also 3D printed parts, roughly 1 centimeter extra. And then here we have a threaded rod, 8 millimeter diameter, which is our main shaft. So these are the main, let's say, 3D printed parts. And as I said, we have this 8 millimeter diameter threaded rod. Why threaded rod? Because then I can put the nuts on this with these wings, and I can fix the bobbin wherever I want, and it will not move. This gives the friction. I can center it, and it's very easy to remove it. So how I remove it is basically I just unscrew these 2 bolts, and then I just slide it out, and then I can remove it. It's like a 1-minute process. So then there is an additional mechanism which I haven't shown yet, but that is behind the feeder. Because, for example, one of the source for the wires can be this kind of a reel. So of course the copper wire is sitting on a reel, and something has to hold that. And then I found this. So this is sort of a fishing reel or fishing wire or fishing line holder. So it holds the similar bobbin, and you can put the fishing line, which you just bought, on this, and then you have your fishing rod, and just run the wire or the fishing line from your freshly bought thing to your fishing rod. So then of course you can use any kind of reel, so we will use it for this, and this one is my experimental reel to test the machine. So you can put it here behind it, like somewhere here, and then it will be close to the feeder, and everything goes very smoothly. But I will design and print some kind of additional holder, so the whole system will be one single mechanism, so this piece can be attached to the other side of this linear guide or to the block, so it will move together with the feeder here. So these are the parts regarding the mechanisms. And then regarding the electronics, as you can see, now we have a different stepper motor driver, because this was previously a NEMA 17 stepper motor, so it was enough to use this DRV8825 stepper motor driver. But now, since I have a larger motor which can run at higher currents, of course not necessarily, we do not necessarily want to run it at high currents, but why not? I just have this TB6600 stepper motor driver. It works with the same principle as the other, but it provides more current. So this one thing is replaced. And I did a few modifications on the software, which I will tell you later. But what I want to show you first is just a quick reminder regarding the software. So how the software works and what is included so far in this version. So now I just started up the microcontroller by connecting a 5-volt power source. So I just connected it to a mobile charger basically. Then we have the welcome screen, and then we can set up the speed, which is steps per second. And now I'm using both motors with 1600 steps per turn microstepping. And in this shaft, this 1.6 means that one turn will be done on the shaft per second. And that also means that this speed is now 60 RPM, so 60 rounds per minute or revolutions per minute. And then acceleration, in fact, I removed that feature. Everything is quite low speed, so we do not need accelerations. So this is not relevant right now. And then we have the number of turns which we can feed. So that will be the number of turns on the bobbin. And then we have the wire diameter, but you have to be careful about it because sometimes they provide the wrong value on the bobbin, like here. So now the dimension is there, and it says 0.45 millimeters, but sometimes that's not true because sometimes they refer to the copper core's diameter and not the whole wire's diameter, because these wires obviously are coated and the coating is not counted. So sometimes this can be 0.47 or 48, depends. So you feed the real diameter here, and that will be important because of the displacement of the feeder. And then we have the pitch, that's not yet implemented, but I will do that. So if you want to have a less dense coil or some fancy geometry, then you can change the pitch, but that is not yet implemented. And then we have the bobbin width, which is the width between these two larger diameter pieces. Or if I can show it on this, so between these two things. And then for this it is 14 millimeters. And then we have the bobbin diameter. So that, yeah, the diameter, it's not relevant for the feeder, but it's relevant when you want to calculate the wire consumption. So that's why I wrote this, because at the end I can calculate the total length of wire on this bobbin. And we can manually move the main shaft, which is this, or the feeder shaft, this, by using the buttons or the rotor encoder. And then finally we have the auto winding, and this will show you the layers left, and then the turns done and the length of the wire which you consumed. So first of all, I show you this thing without any kind of wire. Here I just have a piece of wire just to show the things, how it's built. But I will show you how the feeder moves back and forth. And for that, I don't need any kind of winding, but of course I will show you the winding after that with some more simplistic builds. So I just turn on the power supply. So now I'm feeding 15 volts to both things. They share the power. And once again, the parameters. So this will have 1 turn per second and then 160 turns. And actually, if I calculate the width of the bobbin and the wire diameter, then one layer, so to fulfill one layer, will need 40 turns. So 160 turns means there will be 4 layers of wire on this thing. In another video, I will show you the mathematics, all the mathematics behind these calculations and these kind of numbers. So then we know the width, so that's 14 millimeters, so that is already inside. Diameter is not relevant, but that's 20 millimeters, I measured it, and that's all. So we enter this part, and whenever I press the green button, it will start the feeding. And the positive direction, let's talk about that. So it turns towards me, so this wing will go down and this wing will come up. And the feeder's positive direction is that direction, obviously. So this wire starts here, as you can probably see, and it will end up on this side. And then it goes back here, and then it ends up. And how I plan this video is that I just start it. I will not talk at all, and I speed up this process. So you will see that the feeder will go back and forth, and this will turn continuously, yeah, basically towards me. So this is the direction. So let's press start. So this was the process, and hopefully you could see everything. And here we can see that the layers left is 0 and the turns done is 160. So it completed its work, and we theoretically consumed 10.3 meters of wire. So now comes the real demonstration. So I will need some reorganization here. So I will just rotate this 90 degrees. So the motors will be here. So I can hold the wire source easily with my hand, because this suction cup is not working on my table. So we will do that, and we will see how the bobbin is behaving. And I will also talk a few words about the fixing of the wire and so on and so on. So I take the wire, and first I have to feed it through the entrance hole. So that goes in. And then I pull it through these felt discs. And then we reach the first bearing here. So I just fold it backwards without twisting it. And then another fold. And then I have to remove this disc in order to fix the things properly. So this is the small felt disc. So this is a 2 centimeter 3D printed disc, and then we just have this self-adhesive felt. And actually how it works is just we have them sandwiched together, so it goes like this, and then the wire is in between these 2 discs, and we compress it by turning the nut against this spring. So it's not too much compression, of course, and not too much friction, but it's enough. So now I have the other bearing, and then I come through the nozzle as well. So now everything is arranged here, so I just have to put back this disc first, and then there will be a little bit of struggle with this spring. So now I have to fix the wire in the bobbin, and the bobbin has 2 holes. One is a closed hole, and the other one is like a slit. So here we have 2 slits, but on this, let's call it cylindrical bobbin, there is a hole here, which is like closed down. And then the plan is to come through the hole with the wire. so that will make a smooth transition. So I more or less put in the wire, and now what I have to do, I have to prepare 2 turns. I wrote the software in a way that we already expect the user to manually prepare 2 turns, and the reason behind that is because the 2 initial turns have to be packed nicely in the bobbin, so therefore that has to be prepared by the user, and that's what I'm doing now. So 1 turn is done, and now I'm doing 1 more turn to return. So now there are like 2 full turns on the motor. And if you don't want to turn the motor or the shaft by hand, you can do this with the control buttons, but I do it manually right now. And you can also arrange the nozzle position so it will start parallel with the wire. And then you have to make sure that there is a good tension in this wire, and basically that's all. So everything is fixed more or less. I will hold the reel properly, and I have to make a notice already, or say the notice that this wire was wound like 100 times already, so I'm using this wire back and forth between 2 bobbins to test the winding. So it can be that the dent or the twist on the wire will mess up this thing. But if you are using a, let's say, virgin wire, which is untouched and perfect in shape, that should give you a nice, nicely wound coil. But here we will see what we get. And I will also, before starting this, I will also prepare another camera to give you a close-up picture of the winding procedure. So I prepared everything. I restarted the microcontroller, and I don't change anything. So we will go 60 RPM or 1 turn per second on this part, and then I know that we want 160 turns, so that should be 4 layers, but I'm not sure if we will be able to finish the 4 layers because of the irregularities on the wire surface. And then 0.35 millimeter is the wire diameter. That's more or less fine, and the bobbin width is 14 millimeters. So that will define the, let's say, oscillation distance for the feeder. And the bobbin diameter is 2 centimeters, but that will just give us the information regarding the used wire lengths, so it's not really relevant. So I just turn on the power supply. I enter the menu and I hold down this thing here. So this is the wire holder, and we just start. So everything is prepared, so hopefully this will go more or less smoothly. So as you could see, this was not particularly nice because the coil went bananas in the second layer. So there was some hiccups, and then it seems like that the feeder was a bit behind of the coil, and therefore the wire started to jump backwards. So that can be fixed easily. So I just have to either adjust the speed a bit like empirically, or I have to find a better nozzle which is a bit closer to the coil, so it forces the wire to go in the same way. And also, as I mentioned previously, the wire diameter could be larger than the nominal diameter, which could be the case here. So because of that, the coil was built much quicker than the feeder was moving, because the feeder's speed is perfect. So I checked it and it moves as it should. But the feeder was falling behind a little bit, behind of the coil, because the coil had, or the wire had a bit larger diameter. So therefore the let's say propagation of the coil towards this direction was faster than the feeder. So this could have been one problem. So to, let's say, overcome that problem, it's maybe beneficial to measure the wire diameter and then add that input value to the software, so the software will calculate everything properly. So now it's 0.38, and then this will move a bit faster because then the coil is built also faster. But then, of course, the number of layers will be different and so on, because there will be less turns within one, let's say, width. But you can see that this more or less works, but still the output, so the final result, which is basically the purpose of this whole machine, is not perfect. Nevertheless, I want to show you the updates of the software as well, and maybe you, if you replicate this project, you will find a better let's say, method to move the feeder or create the different kind of codes and so on and so on. So let's go to my computer and see what is changed in the code. So let's look at the code, and I want to clarify that I will not go through the code line by line, because I did that in previous videos. So check those videos and then you can see the changes, and you can see how I changed and what I changed. But obviously I will upload this updated code to my website, and then you can use the code as you want. So one of the things that I changed is the microstepping. So we have the main shaft and then the feeder shaft. So both of them use 1600 as microstepping, and this is used, in fact, to calculate the linear displacement on the feeder, because we will always have steps per second as speed and steps as a distance instead of millimeters and millimeter per second. So these are needed for the conversion. Then the second part of the change is this. So I was wondering if we should use accelerations or not. So I decided not to use them, because we run the motor at relatively low speed, so no acceleration is needed. You don't need to rev up the stepper motor to reach the actual speed. So instead of polling the motor with the .run function, I use the run speed to position function, and then with the main shaft we will move until the number of turns are completed, and with the feeder we will oscillate between the two ends of the bobbin, and that's how we do it. So then this part is the part where we press the green button to start the winding. So what we do here, or what I have done here, in the main shaft stepper.moveTo function, I subtract 2 turns from the total amount of steps, because we do the 2 turns manually in the beginning. So now for example, in this example that I showed in the video, the total amount of turns which was done by the stepper motor was 158, because we already did 2 steps or 2 turns manually, and that is subtracted here, so we account for that. And also for the feeder, we have to make sure that we start from, let's say, like 2 diameters away from the side of the bobbin, and that is handled here. So we take twice the wire diameter and then we also multiply it by the number of steps needed to step that wire diameter. So what happens in this equation, in this part, is that we take the microstepping, which is 1600 steps per turn, and we divide it by 5, which is the pitch of the lead screw or ball screw in this case. And what this does is that it tells you how many steps you need to make 1 millimeter of movement, and in this case that's 320 steps. And then this is 2 times the wire diameter, so 2 times 0.35, so 0.7 times 320 steps will be subtracted from the first layer's oscillation. And then after we defined the steps to do, we have to set up the speeds. So the max speed and then the normal speed is set up for the feeder and also for the stepper. So these are the modifications for this part, and these are also relevant, the speeds are also relevant to the run speed to position functions which we run in the main loop. So then we have this winding function, and this makes sure that the feeder oscillates properly between the two ends of the bobbin. And then if we have multiple layers, then we first enter this once the first layer is completed, and then we flip the direction, so it will be a negative direction for the feeder. It will go back towards the motor, the stepper motor. And what happens here is that we take the steps per layer for the feeder. In this very example is 4480 steps, and then we subtract, actually it's this line, and then we subtract the amount of steps which is needed to step the nozzle by 1 wire diameter. And what I said previously is that, for example, this thing can be empirically modified, and maybe this number has to be 2, like in this part I wrote it in the calculation. So this could be like 2, 3 or something, because we don't want the feeder to go entirely back to the other side of the bobbin, but it can be like a few wire diameters away from the bobbin, and then it can start moving backwards. So this really needs some experimentation to find out. And once we set this command, then we have to set the speed, because I noticed that when you use this move function, sometimes the speed is reset to some random value or some very low value. So I set the same speed again, and this will not modify anything else. If just one layer is done, then that's the last layer basically. And what we do here is, if we have like a half layer or less than 1 full layer, then this calculation will make sure that the feeder will not keep moving towards the other side of the bobbin once the feeding is, or the turning of the main shaft is finished. And then of course if it's finished, then it's finished. So we don't do anything there. So these were the small changes, and I'm planning to make a video about the mathematics and everything behind this winding stuff, also with some hopefully nice illustrations and so on, so these small equations can be understood in a better way. But in this video I just wanted to show you this and give you a small update regarding the project. I feel that 1 or 2 more iterations and this will work, let's say, perfectly. But still I have some problems, seems like, with the feeder's movement. So I have to work a bit more on this and see how I can improve it. I might use a different nozzle or something like that. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.